This session is on the status of ongoing mission and instrument program updates. And our first presentation is by Hilliard Paige, Evaluation of Methods Used to Downlink and Process X-band Data from CatSat. This or this?
Start my timer. All right. Thank you. And good afternoon. My name is Hilliard Paige. I'm a full-time electrical engineer at Rincon Research, but they also sent me back to get my master's. So I'm also a graduate student here at the university. During my undergrad time here, I was heavily involved in the CatSat program. Through my work at Rincon as a corporate partner, been able to dedicate a portion of my time to sort of continue that. And so today I would like to just talk about the really cool and exciting things that have been happening at the UA Tech Park 6.1 meter dish. All right, so I'm going to basically ignore this. Walter, the next speaker, is going to talk to you all about CatSat and the fun journey that's been. I'll leave this up here, but what I really want to get into is just the parts that I've been involved with, which has been getting the data down. So ta-da, it's CatSat. It's a spacecraft. It's in space right now. It's orbiting in LEO. It's just for all intents and purposes, it's a full spacecraft. It knows where it is normally. It knows where it's pointing normally, and so those are two important things to keep in mind. It has batteries. It's got solar panels. It's got a whole bunch of stuff. Yeah, so it's got a full attitude control system as well. However, as Walter will mention in his presentation, part of the spacecraft did get damaged, and that feeds into a little bit about what the decisions that were made and the things that we do today. Getting into the specifics, all scientific data from CatSat is downlinked over our patch antennas or through our X-band link, and there are two ways to get data down from our X-band link. The first of those is through a low data rate 10 gigahertz patch antenna, which was the small one, and so that's usually 4 to 20 megabits per second. The other way is the inflatable antenna, which is yet to come up. We're planning that for very soon. And then next to the small 10 gigahertz patch antenna is a larger 5 gigahertz patch antenna that provides the ability to transmit up to the spacecraft, but it's really a loop back. So it provides a service for the amateur radio community. So if you're a ham, if you have your license, actually just this morning, today, we turned it on for the first time and it worked great. So if you're in Arizona and someone's in Texas or Colorado or somewhere that can also see the spacecraft, you can transmit up to it and have someone else in one of those other places hear your transmission and then talk back to you. So that's really, really cool service that we that CatSat can provide. And now making all this happen is this massive 6.1 meter CatSat design radio astronomy dish. I believe it was part of the Karma array down in California. I think the university got like 9 of these things. And one of them is at Tech Park. And it's just a joy to work with. You get about 54 dB of gain at X-band. And X-band for hams is 10.47, not the 8 that the commercial audience gets. Its current configuration, so if you were to log into it right now from this laptop, you could hear anywhere from 6.5 to 22 gigahertz at the press of a button. However, if you change out some feeds and some lenses and bring your own LNA to the party, you can go up to millimeter wave, so 100, 200, 250 gigahertz, and the gain escalates proportionally. But right now it's configured between that sort of XKU kind of regime. So in terms of how the sausage is made, what makes CatSat demodulation unique? Well, during the design process of CatSat, it was chosen to use a DVB-S2 modulation scheme, and that stands for digital video broadcast signal or service. I don't know which one. 2. Essentially, the satellite video community, the guys where you put the satellite on in your dish and you get TV came together and made a standard for how to encode data. And CatSat, we're going to use that. And that's great, but all those spacecraft are usually out at geostationary orbit where there's no Doppler shift. So the spacecraft in relation to you is not moving. And so that's great because you don't have to deal with the Doppler shift, but CatSat's in LEO and at X-band, our Doppler shift is about 600 kilohertz. And why that's important is because the demodulator that was provided by the program was designed for satellites in GEO. And so essentially it's gonna look at frames coming down and say, okay, great. I got the start of my frame is right here. I'm gonna lock in. I'm gonna look at this, and then the signal is gonna go here, and it's gonna go meow, and it's gonna be like, what's going on? And it's gonna scream and cry and pee its pants, and that's basically what it does. And so this is actually what the demodulator would see if you piped it in. This is coming straight off of basically the dish, and so the signal shows you some really cool things. I don't have time to get into all of them, but namely what we're looking at here is a graph of frequency along the X and time along the Y, and it's some people call it a waterfall plot. Rincon calls it a raster. It's a bunch of FFTs that are stacked on top of each other. In a typical world, this is what your processing flow would look like. You would have your dish, which you would receive RF in. You would condition your signal and down convert it into an IF or intermediate frequency, send it into your demodulator, and then you would get your data on your computer, and the little operator would be so happy because he doesn't know the horrors. And so that's in a sane world. And so going back to what I said about here, this is CatSat's signal path flow. And so you start the same. You have RF going into your down converter. You condition it, you filter it, you down convert it, and then it goes into a Rincon, what we call a DLSR, but it's a L-band software-defined radio that we make, and it can do super wideband stuff. And that gets stored for later. And then after that, you have to remember, so how do you get this into a super nice straight signal? And so the answer is that it's a multi-step cooking process. So the first is you need to know where the spacecraft was at all times during your pass. And some of you may know this, but for those of you who don't, you have to know where you were at all time. And then convert that into from an inertial frame to a non-inertial frame. So you need to know where the spacecraft was with relation to where you are. And then you convert that and change that to a range rate where you need to know how fast the spacecraft is moving relative to you, because that will give you that in combination with your operating frequency will give you your Doppler shift. Once you have your Doppler shift in Hertz, the way to change a signal is to multiply that signal by another sine wave, and you'll get, you will end up with both the sum and difference of the wave that you started with. And so you throw away the difference, and you take the sum and you say, you're coming with me, and then that's your signal. And so that's what we do. And that is this entire jaggly line. And then we feed that signal into the DVB-S2 demodulator. And for those of you saying, Hilly, why are you not just doing all this in real time? And the answer is it's a lot of data to be going over and over through a network. And so it kind of slows stuff down, and you get a much better result if you kind of slow down and take your time. So in terms of the received data that we've gotten so far, some of these come from the UHF link, some of these come from the X-band link, but this is data from our HF payload where we were trying to figure out if it was working or not. And so this is all data that has gone through that entire process of getting demodulated and going to actual data. And so this is just various data that we're using to look at. We have downlinked both images and videos over the X-band link, and CatSat actually won a beta award from some of the pictures that were downlinked. But we've also come a very long way from where we first started. So this was our very first DVB-S2 link, and if you go to the one that I see, it's a lot cleaner, right? So by this point, like, my job's done, and it's the commanding team's job for me to be like, yeah, I'm not really seeing it. And so, like, you can see it doing different things in real time. So like all this streaky data that you see here, that's all zeros. That's the modulation that you get when the spacecraft you have a DVB-S2 frame with zeros. It's just streaky. Where it turns into what looks like kind of snow, that's data that's being transmitted. So and then some other things at peak elevation, at the beginning, CatSat's attitude control system wasn't fully operational. And so as the spacecraft would need to turn, it wasn't quite doing it. So it was kind of undershooting. And so you can see the signal kind of go away. But just some sort of stats to date, over 22 gigabytes of data have been downlinked using this method. We've used multiple mod cods and bandwidths. Right now we're at QPSK 3/5 if you're keeping score. The signal strength that I've seen it indicates that we can support 30 megabits per second at a patch antenna with a 1/4 watt of RF, which is kind of crazy. A single element patch antenna, not like a multi-element patch antenna. But one thing I'm most proud of is the way that Rincon and CatSat have kind of come together to help debug, or the ability to debug when the spacecraft is doing something a little funky. And so for reasons that Walter will talk to, we've had our command and control antenna didn't deploy correctly. And so the UA team added the capability to push telemetry data through the X-band link when it was not designed to do that at all, which requires software rewrites. And so this picture really tells it all. This is the amount we had the same amount of data. It took, Walter, how long? 2 days, 3 days to get that data down?
Yeah, it varied a lot.
Okay, all right. And then it took the X-band link 1.7 seconds. So we took 2 to 3 days of telemetry into 1.7 seconds. I think that kind of speaks for itself. So I'm out of time, but thank you guys so much. So great.
Any questions?